Hello and welcome to the presentation of the paper Selection of Suitable Machine Learning Algorithms for Classification Tasks in Reverse Logistics. I am pleased to present you some findings of my work on this topic. My name is Lickert. I'm from the Institute of Machine Tools and Factory Management at the Technical University Berlin, and I will guide you through this presentation today. First of all, I will discuss the motivation why I researched on this topic. Then I will explain how the concept was developed, which is explained in detail in the paper, and finally I will show how the concept can be applied in a use case. Currently, artificial intelligence and machine learning are gaining importance in research and industry, due to the fact that computer performance has improved in the last years and these methods are applied increasingly to practical problems. But what is artificial intelligence? It generally refers to computer programs that mimic human intelligence. In the research on artificial intelligence, machine learning is a key element. Based on previously entered data, machine learning algorithms can recognize patterns or regularities and can make prediction. Basically, these algorithms can gain knowledge from data. This offers a great potential for many applications. However, most of the users are not expert in the field of artificial intelligence and ask themselves the same question: what is artificial intelligence and what can I do with it? Especially in small and medium-sized enterprises, the lack of knowledge about machine learning is a barrier to implement it. In addition to the lack of knowledge, not only the possible applications, but also the possible solutions achieved by machine learning are diverse and complex. Therefore, my motivation was to facilitate an approach to the topic for unexperienced users. For this purpose, the complexity with regard to AI was reduced, which is why I continue to speak only of machine learning. Furthermore, the topic is approached from the user's perspective. So to say, I have already collected data and have a certain task that I would like to solve with machine learning. This results in the goal of introducing a set of criteria to estimate the suitability of available machine learning algorithms for a given task and for available data. By this, it should be possible for the user to consider if the task can be solved in a basic manner with machine learning and thus makes a first step towards implementation. First, I will explain how I have implemented the approaches to reduce complexity and to regard certain learning tasks based on existing data. To do so, the research only focuses on the most common algorithms and only on characteristics that could be interesting for a pre-selection of algorithms. By pre-selection, I mean a first selection which algorithm seems promising for testing. The whole process of testing and evaluating different algorithms and to establish a learning model is left out of this observation. To reduce the amount of regarded algorithms, I focused only on supervised learning tasks. In these tasks, the learning outcome is predefined. This could be, for example, class labels like spam or no spam for emails. By this, I distinguished 7 supervised learning algorithms, which are support vector machine, naive Bayes, neural networks, decision trees, logistic regression, linear regression, and car-nearest neighbor. For each algorithm, I collected statements regarding their characteristics. For example, this could be for the naive Bayes, easy to understand and to implement, and for the linear regression, that the model can be visualized for certain tasks. These statements were then sorted by similarities. For example, the statements about linear regression and naive Bayes I mentioned before, that the model can be visualized and that the algorithm is easy to understand and implement, are referring to their comprehensibility, or if it is interpretable, how the algorithm derives its outcome. Thereby, 8 criteria for preselection could be detected, which are interpretable, types of data, number of observations, sensibility to outliers, training speed, model stability, prediction speed, and numbers of features. These criteria are explained in detail in the paper. Now I created a table where the statements are ordered by criteria and algorithm. This should provide a clear and comprehensible overview and make it possible to compare between algorithms, which supports a targeted selection. As you can see, not all fields of the table are filled out. This is because not for every criterion a specific statement about the algorithm could be found. Also, the criteria are not quantitative, so sometimes statements could not be made clearly. This is definitely a topic for further research to fill out the gaps in the table. But before I talk about further research, I want to show you how the table can be applied in a use case. The use case is located in the field of reverse logistics. This is a branch of logistics that organizes the return and recovery of used products, which includes all activities that are related to the reuse of products and materials, such as collection, selection, sorting, and reprocessing. These processes have many interdependencies and uncertainties, such as the return time, quality, and quantity of parts. Also, there's little known about return parts, so it could be useful to create a basis of information and to use predictions to decrease the uncertainties. In the specific use case, we have a data record about each return part with 5 features. These are the return date, meaning the day the part was returned to the reprocessor, the supplier, meaning the company that delivered the part, the delivery number, which summarizes parts that are returned at the same day by the same supplier, the original equipment manufacturing part number, which is a number to identify the product in specific, and the part condition, which could be missing parts, deformed, or dirty. A possible learning task for the field of application could be to predict the possibility for the return of a part. By this, the uncertainties about return time and quantity of parts can be reduced and the organization in reverse logistics improved. With the exemplary data record and learning task at hand, requirements regarding the criteria can be expressed. I here address only the requirements I use further for the selection of an algorithm. This is types of data, which can be numerical and alphabetical. For this use case, return date, supplier, and delivery number are normally stored as numbers and therefore numerical, but the part number and the part condition are stored alphabetical. Also, the sensibility to outliers is important because the processes in reverse logistics are mainly manual, so the data is inserted manually, which leads to a lot of typing errors and therefore outliers, so the algorithm should handle outliers. Also, as you see, for training speed and interpretable, there were no specific requirements expressed. This is also possible. The table can be read by column or row. By row, it would be checked if the algorithm can fulfill or not fulfill the requirements. Preferable it is to check by column. In this way, the most important requirements can be regarded first. So in this use case, the type of data is regarded first. Only the nav by yes and the decision tree can interpret alphabetical data, as shown in green points. All other algorithms only work with numerical data. This means that the data record would need preparation to use these algorithms. The next requirement is the sensibility to outliers. Now only the characteristics of the decision tree and the naive Bayes are considered, because the other algorithms were ruled out by the first requirement. Only the naive Bayes handles outliers well. So finally it must be checked if the naive Bayes can fulfill the rest of the requirements, which is possible. And so in this case, the naive Bayes is selected to test on the data record. To sum it up, in the paper, a set of criteria was introduced to compare supervised learning algorithms, and by applying the concept to a use case, the practicability of the concept could be shown. Therefore, the concept has the potential to lower knowledge-based barriers for using machine learning. Nonetheless, further research is necessary to evaluate the repeatability of results and the performance of the concept. Thank you very much for your interest and for staying tuned. I am happy to answer any further questions, and I'm open for considerations and suggestions.